Hi, I'm Debayan, and alongside Dr. Xiaoming Liu and Dr. Anil Jain from Michigan State University, we present to you unified detection of digital and physical face attacks. Face attacks against automated face recognition systems are continuously evolving in both digital and physical spaces. Given the diversity of the face attacks, prevailing methods fall short in detecting attacks across all three categories, that is, adversarial, digital manipulation, and spoofs. This work is among the first to define the task of face attack detection on 25 different attack types across three categories that are shown here. Majority of the works that tackle multiple attack types pose the detection as a binary classification problem, with a single network learning a joint feature space. For simplicity, we refer to such a network architecture as joint CNN. But consider the diversity in the available attacks, from imperceptible adversarial perturbations to digital manipulation attacks, both of which are entirely different from physical print attacks. For these reasons, learning a common feature space to discriminate all attack types from bona fides is challenging, and a joint CNN eventually fails to generalize well even on attack types that are seen during training. We demonstrate this by first training a joint CNN on the 25 different attack types in our proposed grand fake dataset. We then compute an attack similarity matrix between the 25 types. From the figure above, we note that the physical attacks have very little correlation with adversarial attacks, and therefore learning them jointly within a common feature space may degrade detection performance. We propose a new multitask learning framework for unified attack detection, namely UniFAD, by training an end-to-end network for improved physical and digital face attack detection. In particular, we first employ a k-means augmentation module that is utilized to automatically construct auxiliary tasks to enhance single task learning, such as joint CNN. Then a joint model is decomposed into a feature extractor with shared layers F that is shared across all the tasks, and then a task-specific branch for each auxiliary task. This figure shows the auxiliary task creation and the training process of UniFAD. An overview of training UniFAD in two stages. The first stage automatically clusters coherent attack types into T groups. Stage 2 consists of a multitask learning framework where early layers learn a generic attack feature, while T branches learn to distinguish bona fides from the coherent attack in that T group. The first question to ask is, how do we automatically construct these auxiliary tasks? One way to do that is to train separate binary joint CNN on each attack type. However, such partitioning massively increases computational burden because now we have to train and test 25 different joint CNNs. Other partitioning methods, such as randomly partitioning, are likely to cluster uncorrelated attacks, leading to the same problem as the joint CNN in the first place. Therefore, we require a reasonable alternative to just manually inspecting the attack similarity matrix we showed before. Fortunately, we already have a joint CNN that is trained on a single task learning framework that can extract salient representations. Thus, we can apply traditional clustering algorithms such as k-means, which takes a set of feature vectors as input and clusters them into k distinct groups based on a geometric constraint. So once we have k different groups, we can use a multitask learning framework to learn coherent attack types jointly, while uncorrelated attacks are learned in their own separate feature spaces. We construct T branches where each branch is a neural network trained on a binary classification problem. And so therefore we have a final loss that is a combination of a shared loss, which is a global binary cross-entropy loss between all attacks and the original image, and there's another auxiliary loss for each of the T branches. Our proposed grand fake dataset consists of 25 attacks from 3 attack categories. Both bona fide and fake faces are of varying quality due to the different capture conditions. For bona fide faces, we utilize faces from Cassia WebFace, LFW, CelebA, SIWM, and FFHQ datasets, since the faces therein cover a broad variation in race, age, gender, pose, illumination, expression, resolution, and acquisition conditions. Adversarial faces are crafted from 6 different adversarial attacks: FGSM, PGD, DFOOL, ad faces, GFLM, and semantic ADV from Cassia WebFace and LFW. And digital manipulation, we utilize all the clips from Face Forensic Plus, including identity swap from Face Swap and deepfake and expression swapping by face-to-face. We also utilize two state-of-the-art models, StarGAN and STGAN, to generate attribute-manipulated faces in Celebi and FFHQ. And finally, we use the pre-trained StyleGAN 2 model to also synthesize 100,000 fake faces that do not exist in the real world. For physical spoofs, we utilize the publicly available SIWM dataset, which consists of 13 spoof types. SIWM is diverse in spoof attack types, environmental conditions, and face spoofs. In summary, we have 342,000 real images and 448,000 fake faces. Here are the detection accuracy, true detection rate at 0.2% false detect rate on the grand fake dataset. We report time taken to detect a single image on an NVIDIA 2080 Ti GPU. We first report the performance of 4 state-of-the-art adversarial digital manipulation spoof detectors individually without doing any sort of retraining on the top. After retraining those 4 SOTA detectors on all 25 attack types, we find that they generalize better across categories. Unsurprisingly, these defenses perform well on some attack categories, however, while failing on others. We find that our proposed UniFAD performs and generalizes best across all the 3 categories compared to any of the prior methods. We find that UniFAD can predict the attack type with 76% classification accuracy. While predicting the exact type may be challenging, we highlight that majority of the misclassification occurs within an attack's category. Without human intervention, once UniFAD is deployed in AFR pipelines, it can predict whether an input image is adversarial, digitally manipulated, or contains spoof artifacts with 97.37% accuracy. We also ablate and analyze our architecture. Our backbone network consists of a 4-layer CNN. We report the detection performance when we incorporate 0, 1, 2, 3, and 4 layers for early sharing. We observe a trade-off between detection performance and the number of early layers. That is, too many early layers reduce the effects of learning task-specific features via branching, getting to be similar to a joint CNN, whereas less number of shared layers inhibits the network from learning generic features that distinguish any attack from bona fides. We find that an even split results in superior detection performance, which is why we use 50% of the shared layers with 4 branches. Thank you.